Welcome to this lecture on animal behavior. Today, we're going to explore one of the most fascinating and magical phenomena in the natural world, known as imprinting. If you have ever wondered why a baby duckling faithfully follows its mother in a neat little line, you are in the right place. We will start from the very basics, understand the biology, and even look at the mathematics behind how animals form these crucial early bonds. Let us dive right in. To understand imprinting, imagine buying a brand new computer or smartphone straight from the factory. The very first time you turn it on, it asks you to set up a user profile, choose a language, and pick a time zone. Whatever you select gets permanently locked into the system's core memory. In the animal kingdom, a very similar first-time setup happens in the brains of newborn animals. Their minds are waiting for critical input that will shape their entire lives. And once that input is received, it is locked in forever. Now that we have our computer analogy, let us look at a real biological example. When a baby duckling hatches, its brain is like a blank slate, waiting for one crucial piece of information. Who is my mother? Nature has a brilliant shortcut for this. The very first moving object the duckling sees is immediately and permanently registered as its parent. This rapid locking in process ensures that a highly vulnerable newborn instantly knows exactly who to follow for safety, warmth, and food, without needing days or weeks to learn. Building on that intuitive understanding, let us formally define what imprinting is. Imprinting is a highly specialized and rapid form of early learning, where an animal forms a strong, permanent attachment to a specific individual or object. Crucially, this phenomenon only occurs during a very narrow and specific window of time in the animal's early life, which we call the critical period or sensitive phase. Unlike normal associative learning, which requires repeated practice and rewards like food, imprinting happens almost instantly, just by the mere presence of the stimulus. This unique form of learning was first described in detail by the famous ethologist Konrad Lorenz. He famously observed gray-lag geese, noting that if he was the first moving thing the hatchling saw, they would faithfully follow his boots everywhere. He discovered that once this bond is formed, it is generally considered irreversible. The animal will not switch its attachment to another object later in life. This strict biological time window, combined with permanent memory retention, makes imprinting entirely distinct from other types of learning, like classical or operant conditioning. So, why did nature evolve such a rigid system? Imprinting is absolutely critical for the immediate survival of many young animals. This is particularly true for precocial species, such as birds and grazing mammals, which are born highly mobile. Because they can walk or swim almost immediately, the danger is very high. If a baby foal or duckling wanders off without knowing exactly who its mother is, it will quickly fall prey to predators or starve to death. Imprinting acts as an invisible tether, keeping them safe. Beyond immediate survival, imprinting also serves a crucial role much later in life through a process known as sexual imprinting. By imprinting on their parents, young animals learn the visual and behavioral characteristics of their own species, ensuring they seek out appropriate mates in adulthood. This creates a unique challenge in modern wildlife conservation. When raising endangered orphans, humans must be extremely careful. Conservationists often use hand puppets shaped like adult birds to feed the young, ensuring the birds imprint on their own species for successful release into the wild. Now that we understand the biology, Let us look at how we can mathematically model this critical period. Because an animal's sensitivity starts low, peaks, and then fades away, we can represent the probability of successful imprinting using a bell-shaped Gaussian curve. In this formula, P of t is the probability of imprinting at a given time t. P max is the highest possible probability, occurring exactly at the peak critical time, denoted as T sub c. The symbol sigma represents the width of this sensitive window. A larger sigma means the animal has a more forgiving time frame to find its mother. If time t moves away from T sub c, the exponent grows negative, causing the probability to drop exponentially. Let us see this formula in action with a concrete example. We have a species of duckling with a peak critical period at 15 hours after hatching. Its maximum probability is 1.0, meaning a 100% chance, and its sensitive window width is 4 hours. We want to calculate the probability of successful imprinting if the duckling sees its mother exactly at 15 hours. We substitute t equals 15 into our equation. The difference in the numerator becomes 0. Since any number to the power of 0 is exactly 1, the equation simplifies to 1.0 times 1. This mathematically proves that at the exact peak of the critical period, the duckling has a guaranteed 100% chance of imprinting. Now, what happens if the mother is chased away by a predator and the duckling is only exposed to her at 23 hours? We substitute t equals 23 into our equation. The difference in the numerator is 8, and squaring that gives 64. The denominator is 2 times 4 squared, which is 32. Dividing 64 by 32 gives us an exponent of -2. Evaluating e to the power of -2 gives us approximately 0.135. This means that missing the peak by just 8 hours drops the imprinting chance drastically to a mere 13.5%. Physically, this duckling is now highly likely to wander off and perish, illustrating why nature enforces such strict biological timers. Let us look at another example to compare how the width of the sensitive window affects survival. We have two bird species, A and B. Both peak at 12 hours with a maximum probability of 0.9. We will expose both to a mother figure at 18 hours. Species A has a very narrow window with sigma equal to 2 hours. Substituting these values, the time difference is 6 hours. Squaring this gives 36, and our denominator is 8. This leaves an exponent of -4.5. Calculating this yields a tiny probability of just 1%. Because species A has such a narrow critical window, being 6 hours late makes imprinting almost impossible. Now, let us perform the exact same calculation for species B, which has a wider window where sigma equals 6 hours. The time difference is still 6 hours, so the numerator remains 36. However, the denominator is now 2 times 36, which is 72. This makes our exponent -0.5. Evaluating this gives us approximately 54.5%. The final results show a massive difference. While species A had only a 1% chance, species B maintains a robust 54.5% chance at the exact same time. Physically, this means species B is much more adaptable to delays, perhaps because it lives in a less predictable environment where finding the mother takes longer. To bring all of this together, let us look at the visual representation of the critical period. On the horizontal axis, we have the time after hatching, measured in hours. On the vertical axis, we have the probability of successful imprinting. Notice the smooth, bell-shaped blue curve. It starts very low right after birth, climbs rapidly, and hits its absolute maximum at the peak imprinting time of 15 hours. The shaded light blue region represents the critical period, the optimal window for the mother to present herself. As time moves past this window, the curve drops exponentially back towards zero. This diagram perfectly captures the strict, time-dependent nature of this biological mechanism. We have covered a lot of ground today, so let us review the key takeaways. First, imprinting is a rapid and irreversible form of early learning that bridges the gap between innate instinct and learned behavior. Second, it is entirely dependent on a strict biological timer known as the critical period. Missing this window can be fatal. Third, this mechanism guarantees immediate survival by keeping young animals close to their protectors, and it shapes their future social behaviors. Finally, we saw how mathematics allows us to model this biological sensitivity, proving just how vital timing is in nature. You now have a solid understanding of imprinting. Great job!